Now, in this video, we're going to take up one more problem. The problem reads as the problem number 11. The following data pertains to a tensions test conducted in the laboratory. So, the diameter of the test specimen is 25 mm. The gauge length of the specimen is 200. The extension under a load of 20 kN is 0.04 mm. The loaded yield point is 150 kN. Then maximum load is 225 kN. And the breaking load or the load at failure is 120 kN. And length of specimen after failure is 275 mm. And the net diameter is 18.25. And determine number 1 Young's modulus, number 2 yield stress, number 3 ultimate stress, and number 4 breaking stress, number 5 percentage of elongation, and number 6 percentage reduction in area, and number 7 safe stress adopting a factor of safety of 2.5. So first one we're going to consider the Young's modulus. To find the Young's modulus, so what is the condition? The stress is directly proportional to strain within the proportionality limit. So the condition here in the problem he has given for the load of 20 kN, an extension is given and the load is within the proportionality limit. So we need to consider this load for finding out the stress and strain to find the Young's modulus. So what is stress? Stress is directly proportional to strain, which is load by area of cross section, which is P by A. So what is that? For the load of 20 kN, because that is the one which is in the proportionality limit. So 20 into 10 to the power of 3 divided by the area of cross section. The D naught, that is the diameter of the specimen, is 25. So since it is a round bar, so the area of the round bar will going to be pi d square by 4, which is pi by 4 into 25 square. Substitute these two values, and on simplification, you will going to get it as 40.744 Newton per mm square. Then comes with the strain, the change in length by the original length, which will be delta L by L. So what is delta L? For a corresponding proportional limit of this, the extension will be 0.04 and the gauge length is given to be 200. So substitute these values, that is the delta L will be equal to 0.04 and the L length of the specimen is 200. You substitute these two values and then on simplification you are going to get it as 2 into 10 to the power of minus 4. So now what we need to find out is the Young's modulus. By Hooke's law, what is it? The stress is proportional to strain within the elastic limit or within the proportionality limit. So what is the Young's modulus? Young's modulus is nothing but stress by strain, which is sigma by epsilon. You substitute the values of sigma and epsilon in these two formula. So that is 40.744, which is the stress value, divided by the strain, which is 2 into 10 to the power of minus 4. So on simplification, you will going to get it as 203.720 Newton per mm square. So you are going to get it as 203.72 kilonewton per mm square. Or 203.72 kilonewton per mm square, or it can be expressed as 203.72 into 10 to the power of 3 Newton per mm square. So thus the Young's modulus will going to have this particular value. Now we go for the next one, which is the yield stress. So that is what is the maximum load, that is the load at yield point divided by the original cross-sectional area of the specimen. So what is the load at yield point? The load at yield point is 150 kilonewton. So that is 150 into 10 to the power of 3 Newton divided by the original cross-sectional area of the specimen, which is pi by 4 into 25 square. Substitute these two values and on simplification, you will going to get it as 305.6 Newton per mm square. So the next condition is the ultimate stress, that is the maximum load by the original cross-sectional area of the test specimen. So what is the maximum load? The maximum load is 225 kilonewton. So you convert that kilonewton into Newton, so which will be equal to 225 into 10 to the power of 3 divided by the original cross-sectional area of the member, which is pi by 4 into d square, which is 25 square. So on substituting these two values, then when you simplify it, you will go and get it as 458.4 Newton per mm square. So then what is the braking stress? The braking stress will be the braking load or the load at failure divided by the original cross-section area of the specimen. So what is the load at failure? The load at failure is 120 kilonewton. So it will be converted into Newton, which will be 120 into 10 to the power of 3 divided by the original cross-section area, which is pi by 4 into d square, which is 25. So on substituting these two values, you will going to get, on calculation, you're going to get it as 244.5 Newton per mm square. So then what is the true braking stress? The true braking stress is the braking load at failure or load at failure divided by the actual cross-section area of the specimen or the bar at failure. So what is the braking load? The braking load is nothing but 120 into 10 to the power of 3, which is kilonewton. 120 kilonewton as converted into Newton. So divided by the actual cross-section area, which is pi by 4 into 18.2 pi square. So that will be equal to, on simplification, you will go and get it as 458.74 Newton per mm square. So what is the percentage elongation? The percentage elongation is LF, that is the total increase in length by the original length into 100. So what is the total increase in length, which is LF minus L0 by L0. So LF is nothing but 275, that is the 275 minus the original length, which will going to be 200. So they will divide by the original length is 200 into 100. So on simplification, you will going to get it as 37.5% of the percentage elongation. Now we are going to consider the percentage reduction in area. So original cross-sectional area minus final cross-sectional area divided by the original cross-sectional area into 100. So what is the original cross-sectional area? Pi by 4 into 25 square minus final cross-sectional area is pi by 4 into 18.25 square divided by the original cross-sectional area is pi by 4 into 250 square. So 25 square, that is the diameter of the specimen, into 100 is expressed in percentage. So if you take this pi by 4, you can take it as outside and it is going to be get cancelled as it is in the numerator and also in the denominator. So in 25 square minus 18.25 square divided by 25 square, so into 100. So on simplification, you will go and get it as 46.7%. Similarly, the safe stress, which is the yield stress by factor of safety. So yield stress is nothing but the 305.6, which we have calculated here, which is yield stress is 305.6 divided by factor of safety is 2.5. So on simplification, you will go and get it as 122.24 Newton per mm square. Similarly, we are going to take up the next problem. Here, the tensile test was conducted on the mild steel bar. The following data was obtained from the test. So what is that? The diameter of the steel bar is 16 mm. The gauge length of the bar is 80 mm. Loaded proportionality limit is 72 kilonewton. Extension at load of 60 kilonewton is 0.115. Loaded failure is 80 kilonewton and final gauge length of the bar is 104. Diameter of the rod at failure is 12 mm. Determine Young's modulus, proportionality limit, true braking stress, and percentage elongation. So first, what we are going to take up is the Young's modulus. So to find the Young's modulus, calculate the value of stress and strain within the proportionality limit. The load at proportional limit is given, but the extension corresponding to this load is not given. Since for the load of 60 kilonewton, which is within the proportional limit, the extension is given. So consider this load. So here what it says is load at proportional limit is 72 kilonewton, but extension at load of 60 kilonewton is 0.115. So what is the range between, what is the meaning of these two? So normally whenever you are considering the Young's modulus, you have to take the proportionality limit into the consideration. So the proportional limit or the load at proportional limit and the extension at proportional limit. But here the load at proportional limit is given as 72 kilonewton, but he has given the extension at load of 60 kilonewton. So naturally you have to find out the load at proportional limit as 60 kilonewton, and to that you are going to take the extension as 0.115. You cannot take the load at proportional limit and the extension at load of 60 kilonewton. You cannot take like that. So on the 72 kilonewton, the 60 kilonewton is well within the limit of the proportional limit. So you take the stress at 60 kilonewton and also the strain at 60 kilonewton, and then find out the Young's modulus. That is what he does. So consider this load. So what is stress? Stress is nothing but P by A. What is that P? 60 into 10 to the power of 3 divided by pi by 4 into 16 square. That is the original cross-sectional area of the specimen. So on simplification, you will going to get it as 298.4115 for 155, which is Newton per mm square. So similarly, the strain, which is equal to delta L by L. So the delta L is 0.115 divided by the original length of the specimen, it is 80. On simplification, you will going to get it as 1.4375 into 10 to the power of minus 3. So similarly, the Young's modulus is given as stress by strain, which is 298.4155 divided by 1.4375 into 10 to the power of minus 3. So on simplification, you will going to get it as 207,593.4 Newton per mm square. Then we will going to have the proportionality limit, which is loaded proportional limit divided by the original cross-sectional area of the specimen. So the loaded proportional limit is 72 kilonewton. So you convert that into Newton, that is 72.10 to the power of 3 divided by the original cross-sectional area, which is pi by 4 into 16 square. So on simplification, you will go to get it as 358.1 Newton per mm square. Similarly, you can take the true breaking stress, which is the loaded failure divided by the actual cross-sectional area of the bar at failure. So loaded failure is given to be 80 into 10 to the power of 3 divided by actual cross-sectional area at the breaking point. So that is pi by 4 into 12 square. So on simplification of this, so you are going to get this value as 707.3553 Newton per mm square. Similarly, the percentage elongation is given by the total increase in length by the original length of the member into 100. What is the total increase in length? You have the 104 minus 80 divided by 80 into 100. So on simplification, you will going to get it as 30%. So this is how you will be able to solve this problem on the tensile test which is conducted on the UTM, and we found out all the different properties, which is the proportional limit, then the Young's modulus, then the stress, yield stress, breaking stress, and all those things which we have calculated. So this is how you will be able to solve these two problems. And if you find this video is suitable, and please subscribe to this channel. Thank you.